Alright, this video we're going to work on homework 19, or at least get it started. You've already watched the other one to work on this. These transistors are about the same. So here we go. Let's make an NMOS transistor. Start doing homework 19. So NMOS 4 is what we need. NMOS 4, let's throw down a PMOS 4 transistor, and then we'll make our inverter from here. There we go, we'll put it down, F3, draw some wires. Draw some wires there. Put the body connections. Body connections also for the PMOS. Their gates are tied together. Okay, let's get a voltage source. We want 2 of these. I'm going to put it here and here. You'll see, let's see, F8 is move. You'll see why I put this down here below in a second. We'll call this one, right click on it, V supply. It is exactly 5 volts. This one is V pulse, and we'll work on that here in a minute. Voltage supply. Strap it up here. We're going to strap the power source down here. We're going to add a ground node, my favorite one. Spice just has to have it. We can add a ground node here. And we're going to draw this wire up to the gate. Add our capacitor. This is 100 femtofarads, 100F. Oh sure, we'll call this C load because it is a load capacitor. Strap the output to it, and we're good to go. We need to set up this pulse waveform. So we want advanced. It's a pulse. Goes from 0 volts to 5 volts. No delay, a rise time of 100 pico, 100 pico, period of 2 nanoseconds, so it's on for 1 nanosecond, and its period is 2 nanoseconds. There we go, and see how it's stretched all the way over here. So that's really nice. We're going to label these nodes in because it's the input, and out because you know why. Save this here. We're good to go almost. We want to set up some simulations. The first simulation we want to do is we want to simulate V supply. I'm going to go from 0 to 5 volts. Let's go by 1 millivolt. A nice step here. And then also we're going to do a simulation time. We're going to simulate at least 2 periods. So 2 periods plus a little bit more. How about 5 nanoseconds? We don't need to do anything else for this. First we'll do the DC sweeps. We'll have this selected. We'll say OK. We're going to put this down here. So DC V supply. That's our simulation command. Alright, this is all nice. Let's run the simulation. Run the simulation. Plot the input. Plot the output, and that's not what we wanted. You know why? Because we swept V supply, we swept power source. We want to sweep the input. V pulse, much better. Save, run. Excellent. This looks like an inverter. What we want to do is we want to find VL and VH. Those are the easy ones. VL, the output low voltage, actually goes all the way to 5 volts. It turns out you can measure it, but we're going to round it to 5. Same thing, or 0 volts. The input, or the output voltage here goes all the way up to 5. So VL and VH are 0 and 5. Those are really the easy ones for this CMOS stuff. The hard ones to do are VIL and VIH. So an input low is considered anything from VL to VIL, and VIL is where the slope of the output is -1. How do we do that? Well, LTspice is kind of nice. I'm going to right click up here. I'm going to say add a trace. Add a trace, all of our data, the currents and voltages. What we're also going to do is we're going to plot something. We're going to plot D of V out. We're going to plot the derivative, and this derivative is with respect to the x-axis, which is V in. So D V out, V in, and that's the slope of the output. Hey, look at that. Click over here, it's a left click. We're going to tick by 1 and go down to -5 to look at this a little better. So -1 is over here, right at this point, to 1.8 volts or so. The slope is, in fact, -1, and that's the voltage we want. We could put a cursor on this and do the cursor rigmarole, but we don't want to do that. It's too much work, because we may need to do this again. We're going to do put some text on the schematic and ask LTspice to make this measurement. Now, to do these measurements, I'm going to cancel here. If you want to figure out how to do these, go F1, Help Topics, open it up. It's under LTspice dot commands. We're using a dot measure command. We've done these a little bit before. And the one we want is we want to find transient. We want just a number out of here. Transient, find something, find some number when some condition happens. So this is a condition. We need an equal sign there. That's what we want. We want to find the input voltage when the derivative of the output voltage is -1. And that's nice. However, it crosses that twice. It crosses -1 twice, here and here. One of them is VIL and the other one is VIH. That's what this cross parameter is. We can do cross, rise, and fall. We can do some time delays and such. Not really right now. So we're going to add this in here and say dot measure. This stump comes from the DC simulation. We're going to call this VIL. I'm going to find it when find Vn when the derivative of V out is -1. And specifically, we want it to be the first time. I want a new line in here. I'm going to type Control M because that's what it says. You see VIH, find Vn, and dV out is -1 again, but we're going to find it the second time it crosses that. We have to put these measurements somewhere. I'll put them right here. All right, run the simulation. Control L, VIH failed. What's up with that? So 1.8. This is good. VIL 1.8. That's good. Why did it fail? Well, it had something to do with the measurement. Maybe we typed it in wrong. Hey, look at this. V out. Do you see? I forgot to close the parenthesis here. Add that. Simulate again. Control L. Control L is the, click on this, simulation. We want to view the SPICE error log. It's Control L. Here we go. VIL is 1.875. VIH is 3.125. And that's it. Those are the VIL and VIH. In your homework, you have to do this yourself. You can use cursors or you can do these measure statements. Let's say we want to be a little more accurate. Maybe 1 millivolt. SPICE can step by microvolts if we want. Right now we're stepping by just 1 millivolt. Maybe I want a nice accurate simulation. Let's do that. So we're going to step this not in 1 millivolt but 100 microvolts. Run the simulation again. See what happens. It takes a little longer to update and such. Control L. Here we go. VIL is 1.8375. That was, I don't remember the last number, but we have it there. VIH. What's up with this? Do you see how it's the same number? It should be over here. It should be 3 volts or something. 3 point something. Why is that? I'll show you why. On our zealousness to get zoomed in here, let's go to, we're going to show this from -0.9 to to 1 milli and minus 1.1. We're going to really zoom in to this crossing minus 1 point. You see that? So this was Control L again. It was at 1.8735. I'm going to zoom in here again. 1.873, 1.874, right in the middle. And we'll put millivolt axis markers there. Let's zoom out a little bit more here. 3, 2, 5, and 100 microvolt steps. I think you're starting to see it. We're going to mark the data points. So the data points are actually where the simulator happened. Do you see what happened? So we cross 1, but we like go, whoa, it's so shallow zoomed in here that we have numerical precision issues. So it goes down, it goes up, it goes down, it goes up. Well, that's why we crossed this minus 1 point a few times. And that's just numerical precision. We can't, even though we're using double precision floating point numbers in LTspice, double precision is still not good enough. It's not infinite precision. Truly, it only crosses minus 1 twice on this waveform, but it's called numerical noise. So 100 microvolts or microvolts was not really what we wanted. So we'll put it back, run the simulation again. There we go. Of course, we're plotting the data points, which is graphically very intensive. I'm going to shut those off before we have any issues. Control L. There we go. Also, you need to find VOL and VIL. And we found and VOH and the noise margin. It's up to you to figure out how to do those. Next, we are going to also run a simulation for the transient response. We have this pulse. We're going to do transient simulation here. So edit simulation command, transient, 5 nanoseconds. Okay, so we have that down here. Do you see what happened? We commented out the DC because we can only in LTspice run one simulation at a time. Oh, what I forgot to do though, those numbers are actually bogus. I did not right click on here. I want to make these visible. We didn't have our lengths and our widths appropriate. Right click, 1, 10. Maybe I did this on purpose. So control click, control right click, double click here, and control right click, double click, because I want to see the W's and the L's. As a chip designer, that is what I have control over. So I always want to see this on the schematic. I'm not going to run the DC simulation anymore. The numbers that we got aren't going to work for you. They're not for the homework. All right. So what else did we forget to do? Well, we forgot the models of this transistor. Let's put those in. Otherwise, it used default parameters of all these. So NMOS, and it's an NMOS. We can do that. KP. The parameter is KP even for an NMOS. And that's 100 micro. VT0 was 0.6, and lambda was 0.01. Control M. Let's just copy paste this. VTO was minus 0.6, but 40 micro. And we have a PMOS transistor. PMOS. Alright, so that first simulation really was truly hosed. We'll put it here. So we have our transistor models. These are the ones we want. You get different numbers. Alright, let's run a transient simulation. I think we're all set up. Let's run. Run, click the guy who's running. The derivative now we have, it's in volts per second. That's not the trace that we're really looking for. We're looking for rise time, fall time on the output, and then also delay from 50% to 50%. Rise time and fall time are 10 to 90, or 90 to 10. We can do these measure statements again, which are quite nice. Let's do, I'm just going to do the rise time. And this is how we're going to do it. .mes, it's a transient response. tRise is what I'm going to call it. We're going to trigger. Let's go back to the help. So this is all nice. This is the other type of .measure statement refers to a range over the abscissa. That's the x-axis, by the way. The independent variable is a different syntax. So .measure, transient simulation, the name. We can do average, blah, 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 thing. Or we can trigger at a value and target at a value, and so on. So that's what we want. We want to trigger our timer, our clock timer, on the 10% and target our timer or stop our timer at the 90%. I'm going to write this in as a parametric sort of thing. So we want Vout. So we're going to trigger on Vout at a value of, well, 10% of 5 volts, right? It goes from 0 to 5. The span is 5 volts. Why don't we just write that explicitly in case we change the power supply? So 0.1 times VDD. And we'll have to go back here. Let's just leave this here. VDD is not in this. VDD, I need to name this node. VDD. It's this node. Now we can refer to it if we change the power supply voltage. We don't have these parameters in here. It's a parametric simulation. Those are my absolute favorites. So we're going to trigger at this one. We're going to rise, the first rising. I guess we could. We're going to do the second one. We're going to find it right here because we want this simulation to kind of settle down first. We'll get about the same numbers here. But we don't want to take any measurements right here because it's kind of initial conditions and such. We're going to rise the second rise. We need to target this, TIR, G, V, out. It's the same waveform. Value of 0.9 times VDD, rise 2. So we go from, here's the first time we hit that condition, here's the second time, and those are the same on the same waveform. That's the measurement we want. See, OK is way over here. Run the simulation. Control L, tRise, 1.6 times 10 to the minus 10. If we move this over here, this is 163 picoseconds. One thing to note, please, when we're doing special logic simulations, is you see how the rise time is about the same, is pretty close to the rise time that we fed into this gate. We can feed in any rise time into this gate, rise and fall, because it's a pulse source. Really, these inputs to the gates, to logic gates, are coming from the outputs of other logic gates. So we need to set these rise and fall times that we're driving our test setup to be about the same. To do this even better, what we would do is we would use one inverter as a buffer, and then we would copy paste this over here. We would make our measurements on the second inverter. The first inverter would drive it. And now our pulse source with these absolutely sham waveforms don't affect our measurements near as much. We go from fanciful world, ideal spice world, to waveforms that are much more realistic, and so on. That's how we do it. We can do fall times about the same. We can also do delays, but we're triggering and targeting in Spice World for the measurements on different waveforms. Watch out for that. You just use the examples in the help and find it. So here's this. The TD means don't start counting until 1.1 microseconds for this. We didn't use that, we just counted rising and fallings. It really helps if you have the waveform up here when you're writing your measure statements, and that's what I did, and that's how we looked at it. If we say cross or rise equals 3, we have 1, 2, we don't have a rise, we'll get a measurement failed thing for us. That's what we have. Enjoy.